What we do is when that limestone goes into a kiln and making cement, lose 44% of that weight of that limestone to CO2 emissions because there's 44% of the weight of that solid is CO2. That's why it's so CO2 intensive. So what we figured out was instead of just losing those emissions, we capture that CO2 back again with the lime that came out of the kiln to make a reactive form of limestone. And this is the same way coral reefs and shells form in nature. So we kind of took our cues from nature and how nature forms its building blocks. The benefit of that means we park ourselves at a cement plant. We capture the CO2 emission that would have gone to the atmosphere back into product. And what that does for you, it allows you to make 1.8 times the amount of product coming out of the plant. So for every ton of limestone feedstock, you make 1 ton of product. You're basically turning CO2 actually into cement, into stuff that can go into infrastructure. And that's really what makes the economics work. And so by bolting our plant, it's a chemical process we put beside the plant, capturing the CO2. But by bolting our process on, what we make out of it is, this white powder. This is how it comes directly out of our reactor. It's not milled after the fact like you would with your clinker. And the benefit of that powder, it is calcium carbonate. It's 44% by weight captured CO2, but it can be used both as a partial cement replacement, so under ASTM 595 with traditional Portland cement, or we can go all the way to 100% our product as the cement as well under 1157, so under performance-based regulations. And, I think the approach we've taken really is to be beside the cement plant, leverage their feedstocks, leverage their infrastructure, leverage the back-end logistics and sales so that we can put our product out there cost effectively or at the same price as traditional cement.